An infinite sequence a sub n is an ordered list of numbers of the form a sub 1, sub 2, sub 3 to a sub n. The subscription n is called the index variable of the sequence. Each number a sub n is the term of the sequence. Some sequences are defined by the explicit formulas, in which case a sub n equals f sub n for some function f sub n, defined over the positive integer n. In other cases, sequences are defined by using a recurrence relation. In a recurrence relation, one term or more of the sequence is given explicitly, and subsequent terms are defined in terms of earlier term in the sequence. So this often involves the Fibonacci sequence. Example 1. Find the formula for the general term a sub n for the sequence that is given. Note that here, all the numbers in the numerator are increasing by 1. The number in the denominator are exponent of 5. So a sub n equal to n plus 2 divided by n to the 5th. How do we address the negative, the interchanging sign, the changing sign? We start with a positive, right, and then negative subsequently. So let's just check. A sub 1 is equal to 3/5. A sub 2 equal to negative 4/25. Now, if we want to start out with a positive when n equal 1, then we have to change our term to a sub n equal to negative 1 to the n minus 1 times n plus 2 divided by 5 to the exponent n. So let's double check. When a sub 1 would mean n equal 1, a sub 1 equal to 0, a minus 1 makes 0, negative 1 to the exponent 1, negative 1 to exponent 0 makes 0, 1 plus 2 makes 3, 5 to the first makes 5, so it checks out. So this is the a sub n that we are looking for. In the next case, we have 3, 9, 27, 81, 234. That is the, so it seems like we have an exponent of 3. So a sub n equal 3 to the n. Now let's take a look at the denominator. We have 4, 7, 10, 13, and 16. So how do we deal with that? So let's take a look at the denominator alone. We start with 4. 7 is equal to 4 plus 3. Then the next one is 10. 10 equal to 7 plus 3. So seems like we have 4 plus 3 plus 2, right? That 4 plus 3 plus 2, that make, oh, that's 10, right? So that would be, what, 4 plus 3 plus 3? The next one, 13. So that is 10 plus 3. So previously we have 4 plus 3 plus 3 plus 3. So similar, we add in 3 next time here, each time here. So for n equal 1, I'm looking at 4 plus 3 times n minus 1, or plus 1 minus 1. for n equal 2, it seems like I'm looking at 4 plus 3 times 2 minus 1. For n equal 3, I'm looking at 4 plus 3 times 3 minus 1. So it seems like the denominator is 4 plus 3 times n minus 1. So that is our a sub n term. So let's simplify this. 3 to the n divided by 4 plus 3n minus 3. We distribute the 3 over. So 3 to the n times 3n plus 1. So that is a sub n. We want to find an explicit formula for the sequence defined by recursive formulas. So that a sub 1 equal negative 4, a sub n equal a sub n minus 1 plus 6. Okay. So let's write out a couple terms. So a sub 1 equal negative 4. Then a sub 2 will be equal to a sub n minus 1 is a sub 1 plus 6. That make negative 4 plus 6. Make 2. A sub 3 equal a sub 2 plus 6. That equal to 2 plus 6. Make 8. A sub 4 will then equal a sub 3 plus 6. That equal to 8 plus 6. Make 14. Let's try it one more. So a sub 5 equal a sub 4 plus 6. That is 14 plus 6 make 20. Okay. So note that each of this time here, from a to 2, you add 6. You add 6 in each case. Okay. So how do we address to go from 4 to 6? So go from 4 to negative 4 to 6, we actually add in 10. Okay. So we add 10. So this means a sub n equal, let's try this. Each time we add 6, so 6 times n, and then to go from a sub 2 to a sub 1, from a sub 1 to a sub 2 we add 10, so from a sub 2 to a sub 1 we minus 10. So let's check. A sub 1 equals 6 times 1 minus 10. That makes negative 4. A sub 2 equals 6 times 2 minus 10. That makes 2. So that seems to check out. So here we got our a sub n. So how do you go about finding the explicit formula as a sub n term? You would try continuously to write out the term of the sequence until you see a pattern, and you can see if you can make it you can make a sub n term from there. Let's talk about a limit of a sequence. Given a sequence a sub n, if the term a sub n become arbitrarily close to an infinite number L, as L becomes sufficiently large, we say a sub n is convergent, is a convergent sequence, and L is the limit of the sequence in this case. Then we can write the limit at n approaches infinity of a sub n equal L. So if the sequence of a sub n is not convergent, we say that is divergent sequence. Okay, so let's talk about the Zeno paradox. So the Zeno paradox says, when Achilles will reach the position where the turret started, the turret will have moved further ahead. Or another version of Zeno paradox. See, you start at this point, okay, and you want to reach this door. In order to make it to this door, you have to make it to half of this door. Okay, so the distance here is half. In order to make this half distance, you make it a fourth to this door. In order to make the last 1/4, you have to make it 1/8. In order to make it to 1/8, then you have to make 1/16. Continuously keep going, right? So the distance between where you started to where you reach that door is given by this sequence. So that's the Zeno paradox. It doesn't seem like you ever would reach that door, because in order to make it to the door, you keep on dividing half the distance. So how do you calculate the distance between where you were and where the door is? Okay. Limit of a sequence is defined by a function. Consider a sequence a sub n so that a sub n equal f sub n for n greater than equal 1. If there exists a real number L so that the limit at x approaches infinity of f of x equal L, then the sequence a sub n converge and the limit n approaches infinity of a sub n equal L. And we have algebra for limit law. Okay, so you can take a look at it on your own. We have the sequence a and b, a real number c. Then if the limit of a constant is a constant, the limit of a constant multiplied with the sequence is equal to the sequence multiplied with the limit of the constant multiplied with the limit of the sequence. The limit of two sequences, okay, at the result of adding and subtraction, are the same as the limit of adding or subtracting the two sequence itself, so on and so forth. So let's find the limit. Find the limit as the limit at n approaches infinity for 1 divided by n to the r, for r is greater than 0. So here, a sub n equal 1 over n to the r. Now, as n approaches infinity, you're looking at 1 divided by a really big number. A sub n then approaches 0 in this case. So the limit at n approaches infinity, 1 over n to the r, for r greater than 0, is equal to 0. Okay. In the next case, the limit at n approaches infinity of n divided by n plus 1. So here we can consider a sub n at n equal n divided by n plus 1. If you remember what you learned in the limit earlier, we are looking at the case where we have infinity divided by infinity here in this case. So if I just go ahead and multiply the numerator and the denominator by 1 over n, then I get 1 divided by 1 plus 1 over n. And this limit equal to 1 divided by 1 plus 0, that equal 1. The limit at ln of n divided by n. Okay, so note that here as n approaches infinity, ln of n will go approaching to infinity, and n also go to infinity, in this case, I can take L'Hospital rule and I can say then the limit at n approaches infinity equal the derivative of ln of n, that 1 over x, 1 over n I mean, divide by the limit, divide by the derivative of n, that make 1. So now I'm effectively looking at the limit at n approaches infinity, that 1 over n, that equal to 0. The limit at n approaches infinity, the r to the n. So here we basically have a exponential function. So let's consider the case where, case 1, where r is greater than 1, and case 2, where r is between 0 and 1. Okay, so let's talk about case 1. If r is greater than 0, the limit at n approaches infinity of r to the n will approach infinity, right? Because this is an exponential function. In case 2, r is between 0 and 1. The limit at n approaches infinity of r to the n will have to equal to 0, right? Because this is an exponential decay. So recall, we have an exponential growth. The graph looks like this. And exponential decay look like that. So the function itself is y equal a to the x. In this case, for a is greater than 0, y equal a to the x. For 0 less than a less than 1. Determine the convergence and find a limit for each of the following sequence. Determine whether the sequence is convergent or not. If it is, then find its limit. Okay. So first one, we have 5 minus 3 divided by n squared. So we start with the limit at n approaches infinity, the a sub n, that is the limit at n approaches infinity, the 5 minus 3 over n squared. At n approaches infinity, 5 is still 5, but 3 divided by n squared will approach 0, so this is equal to 5. In that case, the limit at n approaches infinity, 2 to the n divided by n squared. We're looking at infinity divided by infinity, so I can go ahead and use L'Hospital rule to take the derivative. Then the limit at n approaches infinity of 2 to the x, 2 to the n, times ln of 2 divided by 2 to the n. Okay. Now, note that we still have the infinity divided by infinity. So we do the L'Hospital again. So the limit at n approaches infinity of ln of 2 times 2 to the n times ln of 2 again divided by 2. This equal to infinity. So here you can see there the sequence is divergent. And in part A, we have convergent. So what if we have the cosine of n divided by n squared? Now, think about this. If I go ahead and take the limit and n approaches infinity, cosine of n divided by n squared, we know that the value of n is bouncing between -1 and 1. Okay, and we have n squared. Well, as n approaches infinity, this will go to infinity. Now, whether we have this is positive or negative, that is two different, that we don't know. So what I know is that the sequence cosine of n is between -1 and 1. Which means -1 divided by n squared is less than or equal cosine of n divided by n squared less than or equal 1 divided by n squared. This means by the squeeze theorem, the limit at n approaches infinity of -1 over n squared is less than or equal to the limit at n approaches infinity of cosine of n divided by n squared and less than or equal the limit at n approaches infinity of 1 over n squared. We know that the limit at n approaches infinity of -1 divided by n squared is the same as the limit at n approaches infinity of 1 divided by n squared, and that is equal to 0. This means that I can say the limit at n approaches infinity of cosine of n divided by n squared equals 0 by the squeeze theorem. Okay, and let's make sure we spell this correctly. There we go. Now, a sequence is called increasing if the previous term is less than the current term for n is greater than or equal 1. It decreasing if the previous term is increasing if the previous term is less. It decreasing if the preceding term is greater. It's called monotonic if it either increasing or decreasing and then no changing in between. A monotonic sequence theorem, every bounded monotonic sequence is convergent. Okay. Here's another definition. A sequence a sub n is bounded above if there is a number m such that a sub n is greater than or equal m for n is greater than 1. It is bounded below if there is a number small m such that m is less than or equal a sub n for n is greater than 1. If it's bounded above and below, and then the sequence a sub n is a bounded sequence. Okay. For each of the following sequence, use the monotonic convergence theorem to show the sequence converge and find its limit. Look at the first sequence. Let's write out a couple terms. to see what happened. A sub 1 equal 4 divided by 1. A sub 2 equal 4 to the second, that makes 16. Divide by 2. 4 to the third makes 64. Divide by 3 factorial, that is 6. So on and so forth. So let's simplify this. We get 4, 8, 32 over 3. So it seems like that each of these terms are increasing, right? Okay. But then, what happened if the third term? So we have a sub 1, a sub 2, a sub 3. Okay. So let's take a look at the next term, one more. So when we talk about a sub 4, we get what? 4 to the 4th divided by 4 factorial. 4 to the 4th make so that's 64 times 4, and that is equal to 256. 4 factorial is 6 times 4 make 24. And then we can simplify this to get 32 over 3. Oh, it seems like repeat. One more, see what happened. 4 to the 5th divided by 5 factorial. So this simplified to be 128 over 5. So it seems like it started out increasing and then decreasing. So we can see that here the sequence increasing for n less than equal 3 and decreasing for n is greater than equal 3. Okay. So this meant that I can write this here. I can say that, okay, well, a sub n plus 1 is equal 4 to the n plus 1 divided by n plus 1 factorial. So this really just 4 divided by n plus 1 times 4 to the n divided by n factorial. So this is 4 divided by n plus 1 times a sub n. Okay. And this is less than or equal to a sub n if n is greater than or equal to 3. So the sequence is decreasing for all n greater than 3. Let's see what happened what happened below. We can see that the sequence is bounded below by 0 because this a sub n, 4 to the n divided by n factorial is always greater than n. It's always greater than 0. So this means the sequence is bounded below by 0 for all n. Okay. So this means the sequence is converged. So it's convergent. Okay. So let's go ahead and find a limit. So let's find the limit of it bounded above. The limit at n approaches infinity of a sub n plus 1 is equal to 4 divided by n equal to the limit at n approaches infinity 4 divided by n plus 1 times a sub n. Well, we know that the limit at n approaches infinity of a sub n is equal to 0. Okay, so then this is equal to 0. Therefore, the sequence is bounded and converged to 0. Take a look at the next problem. A sub n divided by the recursively sequence such that a sub 1 equal 1, a sub n minus 1, or a sub n is equal to a sub n minus 1 divided by 2. Let's first write out the couple term. So a sub 1 equal 1, a sub 2 equal to 1 divided by 2, a sub 3 equal 1/2 divided by 2, that makes 1/4. A sub 4, that then will equal to 1/8. So here we can see that the sequence is decreasing. Where a sub n plus 1 is equal to 1 divided by 2 to the n minus 1, or it is the same as saying, so here we can see that the sequence is decreasing and bounded below by 0 and above by 1. So this sequence is converged. Okay. So take a look at the limit at n approaches infinity of a sub n plus 1. That is equal to the limit at n approaches infinity, the 1 over to the 2n minus 1, and this approaches 0. So the sequence is converging to 0. It's decreasing.